So now we are starting recording, and this topic is Diffie-Hellman key exchange method. But before we speak about this thing, I want to say that why this problem persists. Because in network, or if we want to communicate with you, like I want to send you some message, and I want it to be only known to you, then I need to enable somehow, how to say, encryption of that message. Do you understand? If you make encryption of the message, then it is possible to send it only to the person who understands what is inside there, but the message is encrypted. And the important thing is that we need to have a kind of a possibility that you have one key. For example, you and me, we are exchanging messages, and we have one key that can open the message. But it is important also that this key can be sent somehow, and no one understands how to use it or so. And then there are so many different technologies, but Diffie-Hellman is one of the technologies, and actually it is everything inside. There is mathematics, because without mathematics it's not possible to make encryption. Yeah? And it is based on the fact that if you have, in order to receive the key, you have to apply the function. But if you have this some kind of special keys, then you don't have to. You cannot use it in order to receive the secret key. And here I have two codes, and one of them is easy, another one is difficult, which is close to real application, but one is easier for demonstration. So we will go. I will show you both of them. But here I have a picture which demonstrates how this method works. You can also download it if you want, but let us open this picture. Here you can see very schematically what happens. There are two cats, or two objects, which want to communicate. Usually they are set A and B, but in order to make a kind of more realistic, we call it Alice and Bob, usually. Yeah. So when we speak about encryption methods and decryption methods, we speak about Alice and Bob. Maybe because it's A and B. I don't know why exactly those names were chosen. And let's say this is Alice and this is Bob, and they are trying to communicate. And you can see that the thing is that here is schematically written that we have to firstly agree on several starting numbers which we can use in order to make encryption. And here it is very specific mathematics there. So we have to choose two numbers like P and G, where P is a primary number. It should be obligatory primary. Do you know what a primary number is? Primary number. Primary number. If I ask you, what is a primary number? Who knows? I can show you how it's written. Maybe you can remember what is there. It's primary number. What is primary? It is such a number that can be divided only by itself or one.
Prime number.
Prime, yeah, prime number. So it means that this number can be divided by itself or one. 2, 3, 5, 7, 11, 13, yeah, 17, 19, yeah, 23, and so on. Yeah.
Numbers that can only be divided by itself and one.
Yes, exactly. These are the primary numbers. And we need to know one interesting operation. What is the operation mod? This operation is important, and when we were learning in the computer architecture course, we did it. Mod. Do you remember what is the operation mod? Sometimes it is noted like percentage. Do you know what does it do? If I ask you, for example, 5 mod 3, what will be the result? Do you remember? Mod means from modulo. Do you know what is a modulo?
That gives a reminder, maybe?
It gives a remainder. So it means like, and what is that about? So if we speak about modulo, so how do you think? What is the modulo? For example,
Returns the remainder of the
yeah,
division.
yeah. For example, 125
So 5 mod 3 would be 2.
modulo 23 is equal 10.
And 5 mod 3 would be 2.
Yeah. So how does it mean? So yeah, it should be 2. Yeah, it should be 2. Here should be 2. How do you calculate it? You see, 125 modulo 23 is 10. If you divide 125 you divide by 23, you get 5 integers, and you have what you have there. You have 5 integers and 10 left over 23. Do you see that? And this part is the modulo. So it is the remainder which is left when you divide by the number. And what is important to understand, when you divide by some number, you always, if you divide by 7, you can get 1, 0, 2, 3, 4, 5, and 6. But you never get 7. Yeah? Modulo is always less than the number which you divide by. Do you understand? Yeah? So, and here also we need to write what is the primitive root modulo. So there is, what is modulo is understandable. But now let us try to write what is primitive root modulo. If we take this and Google, what is that? I don't like Bing. I want to open the Chrome. So if you take primitive root modulo, okay, we can take Wikipedia or this one, doesn't matter. So primitive root. For example, here, what do they have? No, yeah, here, for example, 2 is a primitive root modulo 5, etc. And here you can see 4 is not a primitive root modulo 5, because for every number relatively prime to 5, there is not a power of 4. But so you have to understand what is a primitive root modulo. And let us find some good explanation. Maybe here it will be good. It's like in modulo arithmetic, a number g is a primitive root modulo of in such a case if every number a co-prime to n, if every number a co-prime to n. Do you know what is a co-prime? It is like the numbers which are mutually prime. You know what are mutually prime numbers? Mutually prime numbers, they are like, they cannot be divided. They have no divisors in between. Do you understand? Mutually prime numbers don't have divisors. For example, if you have 15 and 5 and 15 and 12, there is a divisor 3, and then they are not mutually prime. But if you take two numbers which, for example, 2 and 5, they are mutually prime because they can be divided only by 1 or 1 by each other, but they don't have common divisors. They don't have common divisors. Yeah, so that's why they are mutually prime. And it means that a number g is a primitive root modular if every number a co-prime to n. So it means that if you have modular, for example, this is congruent to a power of g modular n. What is congruent? It is like equivalent relation. So this is, let's just check maybe some example. Maybe it's better to understand. Look here, there is very good example. You have a number 3. And 3 is a primitive root modulo 7. It means that if you take 3 and different powers of 3, so you take 3 to the power of 1, you get 3, and if you divide by 7, what you have, you will have some kind of number. What is 3 modulo 7? It is just 3, because the remainder is 3. If you take 3 squared, you get 2. If you get 3 cubed, you get 6. If you get 3 to the power of 4, you get 4, because 3 to the power of 4, you see, so it is like that, but it is and then if you have 3 to the power of 4, you will have 5, and 3 to the power of 4 you have 1, and you see these are all the remainders. And what you can see here, we can see that the period of this modulo is 6. If you take 3 to the power of 7, if you take 3 to the power of 7 modulo 7, what do you think it will be? Let me try to calculate. We cannot calculate, we can calculate, for example, modulo. So we can write 3 to the power of 7 mod 7. Let us try to calculate. It is just 3, you can see. And you can see that you start again. If you get 3 to the power of 8 modulo 7, it will be 2. If you get 3 to the power of 9 modulo 7, it's gonna be 6. Yes, it's gonna be 6. You see, they repeat. Do you understand? They all the time repeat. And if they repeat, then you can see that you have a kind of example like that. And if you speak about this table of primitive roots, then not all the numbers have tables of primitive roots. And you can see that, for example, here you have n can be 1, 2, 3, everyone can be divided by 1, so no roots. But if you have, for example, 7, if you divide by 7, then you can use 3 or 5. Only these two numbers will be giving you all these sequences. Do you understand? More or less. It's a little bit of difficult mathematics, yeah? Maybe let us try to practice a little bit, because then we have to find out. So let us take the picture. Where was the picture? Here. Yeah, here is the picture. You can see here is P 23 and G is 5. So how much is 5 mod 23?
5 mod 23.
Yes.
Can we even do that?
Yes, 5 mod 23. Yes, we can do. 5 divided by 23, it will be just 5. You understand? Yeah? So let us try to make it. So
5 mod 23 will be just 5.
yes,
Okay.
5 mod 23 is just 5. Let us now try to have 5 squared, so 25, 5 squared mod 23. How much will it be here?
2.
Yeah, it will be 2, exactly. Yeah. And how we calculate it? You can see here you can do that, and if you speak about this one, so here you can see that you see how they calculate this. For example, 3 to the power of 1, you calculate modulo 7, it is 3 to the power of 0 times 3, and it is 1 times 3, and here it is just 3, it is modulo 7. Here you have what? You can see that this is 9, and here it is like 2. Yeah. What you have here, you're having here the power, and you can see here you have the power 2, and why you are putting here 2? Because 3 to the power of 1 is 2, and then if you have it like this, then here you have something actually. Do you understand?
So since 3 to the power of 2 is 2, we just see 3 to the power of 3 as 3 to the power of 2 multiplied by 3. Therefore, it's 2 multiplied by 3.
Yes, 2 multiplied by 3. But here you have 6.
Because 2, 3.
It is, yeah, it is 6. You see? Yeah. And this is like that. And here all the time, this is 3, and this is why 3 you have. And here you have 2, so these 2 you just calculated. And then later you can guess already, yeah? Let us try to see this 23. So we have to understand the algorithm, so we need to train that. So here 5 mod 2 is 5. Do you understand why? Yeah. Now 5 to the power of 2 mod 23 is 2. Do you understand why? No. 5.2 is 25. 25 mod 23. Yeah. So what you have? You have 1 and 2 over 23. Yeah. So 2 is the rest. Yeah, the remainder.
Basically, 25 slash 23, so we have one whole.
Yes. 25 slash 23, then 1 is the unit, and then 2 over 23. It's 1 plus 2 over 23, yes? Okay, so this is clear why you have 2. So now let us try to have the theory. What will be 5 to the power of 3 mod 23? What will be the result?
2 by 5, 10?
Yes, it is 10. So here you can see it is 2 by 5. Because it is this one is 5, but this one is 2, and then you multiply. Now what about 5 to the power of 4 mod 23? What will be the result?
It cannot be 50.
It cannot be 50.
So if it is, so 10 multiplied by 5 is 50, which in itself is like 23 twice.
Can it be like 4 maybe?
Yeah, it will be 4. Because,
let us try. Yeah.
In 50 we can fit 23 twice.
Yeah. Let us try. Just check. We have to take this. So here we'll have 5 to the power of 4 mod 23. So just it's 4.
Yeah.
So now what is 5 to the power of 5 mod 23? 20. Yeah, 20. We can double check so that we can be sure about this. 20. What is 5 to the power of 6 mod 23?
100 and 23.
It's again 20, no? No, it can't be 20.
Wait a minute.
It should be 12.
Wait a minute. 92 should be 12, you say?
It's 2 to the power of 5 times 2 to the power of 5
Yeah,
times
yeah.
2 to the power of 5. It's 8, sorry. It's 8. Should be 8.
Yeah, it is 8.
It is 8, right. So you were right. Yeah, I was wrong.
But yeah,
So,
we can also just do that.
yeah, it is 8. You understood it, guys? Yeah. So let's make it one more time. So because you have to understand it better. So this is
I mean,
5.
I was counting it. I said I thought it was 8, and you said 12, and I was.
Yeah, yeah. I was.
doubting.
Yeah. So that's why. Yeah. So you were right. So here 7. What is here? Mod 7. Mod 23. 5 to the power of 7.
40, but it can be 40. So
It can be 40. Yeah. It can be 40.
17?
17.
I think 17.
Yeah. Let us check. Yeah. I also think 17. So here it is 17. Now you started to understand. So what is 5 to the power of 8 mod 23?
I would say that it would be 8. Because 5 to the power of 4 and 5 to the power of 2. 4 and 2.
Maybe 16?
Hmm. 16 is
Because it's 5 to the power of 4 times 5 to the power of 4.
Is it? Oh yeah, yeah it is. Right.
I think here. Let us
Yeah,
check.
16, I agree.
16.
Yeah, I agree. I forgot how powers work.
Yeah. Okay. So now 5 to the power of 9. What is mod 23?
8, but it can't be 18. Therefore,
You can yeah. So
9,
it can be this.
17, 9. I think it's 1.
Hmm?
It's 1.
1.
I think it is.
Let us try to take it. So 5 to the power of 2. No, it could be, we can take this one 16
Yep.
times 5. It's 80.
Times 5. Yes,
80.
it is 80.
80.
And then 23 by
23 by 3.
9.
69. So it's
79.
11.
79. 23 by, by 3. Yeah, it is 69.
So it's 11.
11, yeah.
11. We can check. It always helps understanding when we check. It's 20. Yeah, 22. Why? But wait, I put 11. Yeah, I put not. I didn't put 9. Sorry, it was my mistake. Because it's 11.
Yeah.
Okay. Now 5 to the power of 10 mod 23.
23 by 2. 56. So, 55 times 46 would be 4, 9. I think 9.
9?
I think 9.
Could be 9, yeah. I agree. We can check again. Nine. Good. And the next thing is 5 to the power of 11
So kind of that's more, yeah.
mod 23.
22.
22.
Yeah.
Because it is this times 2. Yeah. Okay, 5 to the power of 12 mod 23. What is the result?
Hmm.
12, it is 3 times like this. It should be 12, I
I
think.
think. Do you think it's 12?
Because it is 4,
I think it's 18.
3 times.
Maybe 18? Or no?
Let's check. 5 to the power of 12.
18?
Yes, you are right, but
Because 5 by the power of 10 and 5 by the power of 2 is like the least number. So
yes, you are absolutely right. Yes. 18.
Mm,
Yeah. So the next thing is, but interesting is you have to take this. Yes, okay. Now 5 to the power of 13 mod 23. What is the result?
I mean, 69, 21.
21. Yes, let's check.
I think it is.
21. 5 to the power of 14 modulo 23. What is the result?
13.
32 cannot be because it's larger than 23.
13.
It could be 13, you mean, yeah?
I don't think it's even 32 because let's take a 5 to the power of 10 and a 5 to the power of 4. It's 9 times 4. It's 36.
36, yes.
36
So this
times
13, yeah.
23 is 13.
Yes, let us try 14. It's 13, yes. Good. Now 5 to the power of 15 mod 23. What's the result? Two, yes. Two? I don't think so. Two. 5 to the power of 15. Because here, what we have 5 to the power of 15. Hmm? 8. What could be there? Hmm? Eight. So what do you think about that? It's 5 to the power 9, and this made together will be 15. It's 88. 88 and divided by 23. How much will it be? 19? Maybe 19. If you take 15 here, it's 19, yeah. 19. So 5 to the power of 16 mod 23. What will be the result? What will be the result? Of 16.
16.
Yes.
6, 8.
6 and 9. You can take 6 and 10. It will be
72.
72. 72. It will be something like 69.
69, 72.
3. Yeah.
Easy.
Yeah. Let's check. It's 3. Now 5, 17 mod 23. What will be the result? It's 15, yes?
17, 16
Times 5. 15. Should be 15. Let's check. Yeah, it's 15. Now 5 to the power of 18 mod 23. What will be the result? We have to take all of them, so we have 5 more left, yeah? How much is here? Maybe it will be 6? Is it 6 maybe, no? I think it's 6. You can check. Yeah, it's 6. So 5 to the power of 19 mod 23. How much is there? 7? I think 7, but let's check. Yeah, 7. Then 5 to the power of 20 mod 23. How much you think is there?
81, I think, and 81, 69.
It's not 12?
Yeah. No.
12, yeah? 18
yeah,
times
12.
12. Let's try. 12. So now 5 to the power of 21 mod 23. How much is there? So if you take this 21, it's 14, right? 14. Take 21, it's 14. And let me check the last one, 5 to the power of 22 mod 23. How much is this? How much is that? 23, so it is like, what could be there? What is the result? Maybe 1? Let's check. It's 1. And what is interesting, what will happen if you take 5 to the power of 23 mod 23? What will be the result, guys? It is 5. Do you see that 5? Do you see that it is 5 again? Because here you have 1, and after this you will have to multiply it again by 5. You will have again like this. Do you understand it? A little bit. Started to understand, yeah? So this is, you understood it more or less, yeah?
I mean, it's easy.
It's easy, but not always these numbers are the following. These numbers are different. And 5 and 23 have such problem. But if you take, for example, 5 and 21, we can take, for example, I don't know, different numbers, but we will not be able to take the same. So if we take, for example, I don't know, 13 and 7 or something, maybe we will not receive the following, because here it's important to have primitive root, and you can see that 3 and 7, they also are of the same nature, because when you divide 3 powers of 3 by 7, you always receive all the possibilities here. Do you understand? All the possibilities. So all these numbers are below 7, and they are all different, starting from 1 to n minus 7, to 7 minus 1, to 6. And there is a table. You can see that if you have mod 14, and there is nothing interesting. But here is a table, and you can see that if you have, this is like what you divide by, but these are the prime numbers. Oh, no, these are different numbers. And you can see here, if you have, for example, 3, it will be primitive root modulo 4. Because when you divide by 4, you will receive all the possibilities. And here you can see that modulo 23, there are these numbers which can be divided by 23, and they will give you the same property. But, for example, divided by 20, it is not possible. Divided by 18 is still possible. If you have 5 divided by 18, you will have all the different possibilities. Do you understand? Yeah?
Yes.
And now look, let's return to the picture. So here is Alice and here is Bob. And they have to agree on these numbers, on these two numbers. Firstly, there should be the number P and the number G. So G is a base and P is the power. So it's like not a power but the prime number. So you get the prime number here, and this is the base. And now you can do the following. You can think about a secret number which is less than 23. You can think about any secret number which is less than 23. Is it understandable? And then if you take this stuff and multiply it and take to the power, so if you take the base and take to the power of your number, then we can try to experiment with the following. So we have chosen, for example, this part. Let's return to our notepad. So we have the table, you know. We have chosen, now let us choose different different numbers. We have chosen power will be prime number was 23, and I think what was the, let us check. We have and the base was 5. Yes, base G is 5, and this is the prime number. So what we can do, we can receive, you see what we can receive? We have to select a secret integer, each of us. We have to select a secret integer. So we have, I have selected one secret integer which is equal 7. But another person can select a secret integer which is equal, for example, 3. Okay? But this secret integer shall be always less than the power. Understand?
Both numbers have to be less than the prime.
But we can make, actually, it doesn't really matter. We can try also larger. It doesn't matter. You can select any number for secret for secret thing, and then you can calculate these things like A and B. So we have to calculate A. This is the so what we can do, we will take the base G into the power of A and take mod P. Is it understandable? And then we calculate B is equal G to the power of B mod P. Look in the picture. it is that, and this is that. Understandable? And now you can you can freely send it. You can freely send it because we have agreed on those numbers. We have agreed on those numbers, this and that, so we can choose any number. It could be our message. We can send it like this. And what we can do afterwards, when we do so we have different passwords, each of us. Yeah, secret word. We have different passwords, each of us. But afterwards, when we have entered passwords, then we can produce the following, and we will receive some number. Let us receive this number. So we have 7 and 3. What will be A? 17.
Yeah.
What will be B?
To the power of 3 is 10.
10. Yeah? Okay. And now look what we do. We exchange those guys. And then we have the secret key. The secret key is the number we receive and divided by p. So what we do, let us try to see. So now Alice received which number? Alice received 10.
Yeah.
So Alice will receive 10. It will be 10 to the power of
Our secret integer.
of 7 mod 23. And Bob will receive 17, but it will be to the power of 3 mod 23. Let us check the calculator. So let us check this one. It's 14, yes? So Alice has 14. And what has Bob? 14. You see? This is the one common key. Do you understand? Yes? What is the algorithm? You have to choose one and these two numbers, and then you can calculate what will be the common key. Yes? Now let us take the very simple algorithm, how it is implemented. So we have here Diffie-Hellman. Let us download it. And let us open it in Notepad++. So this is and we can launch it in Java. Yeah. Let us copy that now, and let us launch it in Java. So let us create the main class. And this will be the new name of the main class. What happened? Everything okay?
Yeah.
Okay. So let us now try to calculate. You see here we can, it is very primitive program. We can try to figure out how it works, but here we have prime number we define, generator value or base we define. We define also the private key for Alice, the private key for Bob, which can be any numbers, and then we have the secret key which is the same. Do you understand? Now we can try. You can try to launch an experiment with this program, because everything that you do, you can change this number, you can change this number, you can change this number and this number, and you will always get one and the same here. Yeah? But what is the condition of these numbers? Because these numbers you can take any. But what is important to be these numbers? This should be primary number, this should be prime, and you have to take it from the table. You have to know which are these, because there is one special condition that these numbers shall be primitive root modulo. So the generator should be a primitive root modulo the prime number. Yeah. So please try to download this program and a little bit experiment. Try to put different numbers. For example, here let us try to take 22. It is not a prime number. Let us try to launch it. Let us see what happens. It's the same. So, but if you try to make here, for example, 2, what will be here? You see, it's different. Yeah. So it means that it works only for primary numbers. It also, for example, make 19. It's still okay. But if you make, for example, here 7, it's still okay. If you make here 5, still okay. If you make here 2, still the same. But you see, it all the time gives you 1, for example, or something, yeah. And take 100. You see, it's different. So you have to figure out which numbers to take, but you have to keep to this rule that number which is called here primary number, and this is the primitive root for prime generator is chosen, the primitive root, and the primitive root for the generator should be chosen. Yes, so you have to choose the primitive root. Is this understandable? And the primitive roots can be taken from the tables. You can see, you can get, for example, if you take 19, you could take 2, 3, 10, 13, 14, 15. For 22 you could take 7, 13, 17, 19. For 23 you could take the following. Is it understandable? Yeah. For those numbers, these are the primitive. So with these numbers everything works. So you can choose this following. I can check, for example, 25 and 8. Let us take 25, 25, and 8. It doesn't work, you see. Why? Because this is not primitive not prime number. We have to choose the prime number also. It's primitive root, it works, but it's not prime. But it should be prime and primitive root. So this number is good. So if you take any number of this, for example 21 and 31. So here 31, here 21. This shall work. Let us check. Doesn't work. So here a primitive root for because no wait, 21 is yes, a primitive root for prime number, but it should be also, I think, prime. And then which was the 31? You can take 13, then it shall work. No, still very strange. So here 31 is the root number. Yes, maybe it is the both passes agree on the public key generator and prime, so a prime number is chosen and the generator. And here 6 and 15. It could be any numbers here, but so here we have very interesting. Should be the same. Yes, so it's like 2 and 1. But okay, if I change it by places. Yeah, it works when you change by places. You see 12 and 12, so I needed to change by places. Yeah. So generator is...
What do these secret keys do?
Hmm?
Like, what do these secret keys do?
Secret keys?
Yeah.
This could be like a password, for example, for that. So this is like you can you can think about any number.
But it's like so we can use these secret keys to access like the original private key, right?
It's not exactly like this, because the secret key, this one, it can be open. No, it can be just. It is used. It is used for encryption and decryption.
Yeah.
And that's why it should be one and the same. And then the secret key should be one and the same, so you can because you can calculate it on both sides. You have chosen two numbers, yeah. And you exchanged information, which is seen to everyone, which is like A and B numbers, small ones. You exchange it. Everyone can see that. But when you receive other information, you put it to the formula, and you receive one and the same key. So you can use it for decryption and encryption. And you don't need to say that key, because that key is one.
Yeah, both. Okay.
Do you understand? This is the main idea, because you exchange different keys, but you get finally the one. And this one is generated independently. It is not sent anywhere. For example, you have a code calculator in the bank, you know. You're making some numbers there, and at the same time it's not connected to your machine, but it makes the same. Somehow like this, yes? And how is it calculated? So there is also an algorithm, something like that. And here is the same principle, similar principle, that you exchange a key before, and then you can exchange some numbers, but these numbers later generate you one and the same key, depending on where you are. So this is important. Is it understandable? Yeah. Now try to find some. Have you taken this program and try to find it? Can you just think about different pairs when it works? So you can also Google this table. It means this primitive root modulo, and then primitive root modulo, table of primitive roots, and then you can see.
Is it also possible to generate like the primitive root modulo?
For some numbers they exist, and you can use them, but not always they exist. You can check also, but it could be difficult to check. So here on 26 and 15. 26 and 15. Here 26. Here 15. But this one will not work because here is not prime. Yeah, this is not, that doesn't work. But 26, you can have 11. This shall work. No. (26) and 11. Here, the primary number 26, and here 23, and generator is 5. It's like something like this. Prime number could be this one, and generator is here. So here 31 and 11. And like this. And you can see this is very simple program because to demonstrate, but no one uses such simple numbers because these numbers are small, and you can have something like very big numbers, and you can take another program which is located in the same place. So here let's take another program. And let us launch that one. So we need to open one more. This is between two. This is taken from official Java web page, and we have to make this class. Okay, so here I just copy that. And launch it. And here you can see how the keys really look like. If you have, for example, 2048 bits, this key will look like that. You can see Alice secret key and Bob secret key, and they are the same, but the keys look like that. So they have on hexadecimal numbers, And you can see this is a very long key. Such keys could be generated, but this is 2048 bits. Usually in Wi-Fi we have 128 bit AES key. Do you understand? Yeah? And then we can generate it like that. And in Telegram we also use, when you open Telegram, when you create a kind of a connection, when you call each other, there are some kind of symbols appearing, and they're all the time different. So this is also about the key. Understandable? Okay, so this is more or less like that. So maybe it's all for today. It's too much information. Yeah. Here you have the task also. Let me see. You have to task for Diffie-Hellman. There's someone already explained how Diffie-Hellman works. An example of programming languages. Record the video demonstrating an algorithm. So here someone already submitted, but you can also try to create the same. Yeah. Okay. Today we finish.